We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are wicked inventions. Coming up, turntables. What is the connection between wax, tin foil, and your favourite records? The fuel cell. The technology which could see cars polluting the earth with little more than water. Baseball gloves. The fascinating story of this enigmatic sports equipment. We reveal the surprising science and amazing manufacture behind these wicked inventions. The turntable is older than you might think, and we're going to find out how tin foil and wax led to its creation. To trace the history of the turntable, we have to go back as far as 1877, when Thomas Edison, an American inventor, created the phonograph. It was a device that inscribed sound waves onto a cylinder, firstly made of tin foil and later on wax. Crucially though, the phonograph could also play back the recordings by means of a stylus that traced the sound waves and amplified them through a horn. In the 1890s, Emil Berliner came up with the idea of using flat discs with a spiral groove, which ran from the outside of the disc into the centre.
He established the gramophone, and a lot of people will have heard of that name.
The record player was born, and once electricity was added, the motions of the stylus were converted into an electrical signal by a transducer. This was then amplified with a power amplifier and converted back into sound by a loudspeaker. Vinyl records were the dominant audio format throughout most of the 20th century.
Originally, the records were made out of rubber, and then they started using a material called shellac, which is a type of resin secreted by a lac bug. And then eventually they moved on to using vinyl, which is something that lots of people are very familiar with.
In the 1970s and 80s, magnetic cassette tapes grew in popularity. And then when digital formats such as compact discs appeared in the mid-1980s, demand for vinyl records and turntables declined. However, the format was very much kept alive by enthusiasts and, more crucially, DJs who preferred the touchy-feely physical analog format to create their music. The vinyl format has even seen a resurgence in recent years, with many artists re-releasing their music on vinyl records. The record deck is not a new invention, but has seen a resurgence in popularity. This factory in the USA has started making a brand new design.
We are U-Turn Audio. We make the Orbit turntable here in Woburn, Mass. We started in 2012 with a Kickstarter campaign where we launched the Orbit, and since then we've been making turntables ever since.
A record deck is a precision instrument with a lot of sensitive parts. A high level of attention to detail is required to bring all of the elements together into a good sounding, quality product.
It takes around 65 minutes from start to finish to make an Orbit turntable. We don't make one at a time. It's a group of about 12 people that are involved in making one turntable. And so with that we make about 60 to 80 turntables every day.
Coming up, we'll find out how a wobbly camera is the quality secret for this turntable. But first, every turntable starts with a blank plinth. The plinths are made using a CNC router to drill the hole patterns. The hinge holes are drilled by hand in the factory. The plinth is then inspected closely for blemishes. The components are then installed onto the plinth. The circuit boards are screwed into place using a powered torque screwdriver. 3 rubber feet are also attached to the underside of the plinth using screws. The plinth is cleaned using alcohol, ready for the nameplate installation. The plinth is put into a jig to line up and hold it in place. The nameplate is attached to a press which applies it to the plinth using pressure. Whilst the nameplate is being applied, the hinges are installed using a powered torque screwdriver. The power switch is clicked into place. A separate team worked the assembly line for the tone arm production. They worked together to solder the tone arm wires, assemble the pivots, and install and calibrate the cartridges and counterweights. Tone arm assembly requires a high level of skill and attention to detail.
There are about 20 different assembly stations that go into making an orbit turntable. One of the more complicated assemblies is the tone arm, where we have 4 assembly technicians that work together to create that sub-assembly.
Next, the tone arm is attached to the turntable plinth. The turntable is turned upside down in a jig. Then the wires from the tone arm are soldered onto the printed circuit board, commonly known as a PCB. The soldering iron heats the solder at 580 degrees Fahrenheit. The motor assembly is then installed on the plinth and connected to the motor PCB. A bench lathe is used to machine the spindle so that the platter sits perfectly flat. The spindle and platter are then installed. A special camera is used to check that the rotation of the platter is smooth and free of wobble. If there is too much wobble, the platter is rejected and a new one is selected. The turntable is then plugged into an amplifier, and all of the elements are checked for excessive vibrations, as well as checking that the tone arm produces a good quality sound, free of unwanted noise. The turntable is then placed on a burn-in cart, where each table will run for at least 2 hours before going through a final inspection. The very last step is listening to a portion of a familiar record on the table. Only then can we be certain that it is ready to ship. Then it's off to packaging and shipping. Boxes are built, accessories are bagged, and turntables are polished, labelled and sent out to customers across North America and throughout the world.
You used to buy an actual album, and then it was a CD and then digital files, and now you don't even own anything. Most people just stream with a subscription. So I think some people wanted to get back to the actual ownership of the music. I think it's more about, the tangible aspect of owning, a piece of music. It's not kind of lost in your digital library. It's something you can actually have on your shelf and look at and appreciate for a long time.
With transportation responsible for 1/4 of all pollution from fuel consumption and 15% of man-made emissions, it is not surprising that there has been a large drive to create greener technology to power our cars. Electric vehicles seem to be the answer, but powering them efficiently is a problem that the best minds in the world are still grappling with. But fuel cells might be the answer. A fuel cell is a device that generates electricity by a chemical reaction, with hydrogen fuel cells promising a source of electrical power with just drinkable water as a byproduct. As hydrogen is recognised as the most abundant element in the universe, but a pure form of the gas is hard to find down here on Earth, surely this is the stuff of science fiction. Indeed it was, but this technology is here today and might just be powering you down the road very soon.
Jules Verne's Mysterious Island in 1874 described the basic components of a fuel cell. One guy asks another, what we're going to use in the fuel in the future? And Pencroff says, we will be using water. We'll take it, split it apart into hydrogen and oxygen, and those hydrogen and oxygen will be burnt and used as fuel. That water will be the coal of the future. Bear in mind, this is 1874. No one really understood how this worked or even how it was possible other than you burn hydrogen and oxygen and you do get water. That was the first real understanding of how a fuel cell should work, although it was understood more as a combustion engine.
Arguably, Jules Verne could be seen as something of a visionary. But in fact, he was relating a technological theory first put forward by British physicist William Grove in 1839. Grove found that electricity could split water into its constituent parts, hydrogen and oxygen, and suggested it should also work in reverse. Combining hydrogen and oxygen should give electricity. And he built the world's first fuel cell to prove it. By the time Verne was putting pen to paper, however, the internal combustion engine had taken the world by storm, providing power in a far simpler and cheaper fashion than any fuel cell. The fuel cell may have lost the race to power the last 200 years, but how did it work? Every fuel cell has two electrodes, one positive, the anode, and one negative, the cathode, with an electrolyte or membrane that sits between them, and a catalyst which speeds the reactions at the electrodes. Hydrogen atoms enter a fuel cell at the anode, where a chemical reaction splits them into positively charged protons and negatively charged electrons. The electrolyte carries the positively charged protons from one electrode to the other, while preventing the negative electrons, which travel by a wire to the cathode to rejoin the protons. The movement of the electrons provides current that can be used for power. Oxygen entering the system at the cathode combines with the hydrogen and forms water that finishes off the whole process.
That's the basic principle of how it works, but it took a long time between the original understanding in the 1830s to the 1940s to build a prototype. The problem being, for most people, is that getting a decent source of hydrogen and a decent source of oxygen to combine and produce electricity, the understanding of membranes wasn't good enough. If we moved forward to the 1940s, still nothing had actually happened. There was no vast improvement on how do we build a fuel cell. Thomas Bacon started to work out that you needed a membrane, and that if you bring pure hydrogen on one side and pure oxygen on the other side between two electrodes, you can start to use the system to do electricity.
Based in Cambridge in the UK, Bacon successfully developed a 3 kilowatt fuel cell powered by hydrogen and oxygen that used a liquid potassium hydroxide electrolyte, and he demonstrated it on an electric forklift truck. So, why didn't the post-war period go fuel cell crazy? The answer? Cost and complexity. The fuel cells needed to use incredibly pure forms of oxygen and hydrogen, or trace gases could poison the electrolyte and destroy the electrodes. The cells also used highly expensive materials, such as platinum, as catalysts that stopped their widespread adoption. However, NASA's post-war space program had no such financial worries, and they jumped on Bacon's cell as a perfect way to create drinking water and electricity on board their Apollo missions. NASA improved Bacon's design, and these alkaline fuel cells were present from the Apollo to Space Shuttle missions. NASA have also explored the use of proton exchange membrane fuel cells, or PEMs. These fuel cells replace the liquid electrolyte with a Teflon-derived membrane, which creates lower operating temperatures. Today, PEMs are being built with more cost-efficient materials and the ability to use air instead of pure oxygen, creating the perfect complement to solar power.
Space Shuttle, as it orbits the Earth, will see sun for half the time and darkness for the other half of the time. During the other half of the time, you can either be charging batteries or you can be using a fuel cell to provide the additional power that the systems need. So NASA worked out that if you have a membrane that allows protons to run through, you can actually improve the efficiency of a fuel cell. That membrane is a porous material, a fabric of a kind, and it's filled with an electrolyte, which is basically a liquid with lots of ions in it, so positively charged items. The electron can't move through that, but this allows the positively charged proton to move through it. So the combination of solar cells and fuel cells has allowed the Space Shuttle and the International Space Station to be kept alive and working.
The fuel cells powering electric cars today are primarily based on the PEM design. Hydrogen provides much denser energy than petrol. Just over 5 kilos of hydrogen delivers a 300+ mile range for an average car, about twice the output of an equivalent amount of petrol. So the future is bright, but the technology is still expensive. Once a cheaper alternative to platinum and a safer way to store liquid hydrogen is found, then we might all be travelling the world, polluting our atmosphere with nothing but water. Can we make our own reverse fuel cell with a few household items? We're going to need platinum or platinum-coated wire, a lollipop stick, a 9-volt battery and battery clip, electrical tape, a Pyrex glass of water, baking powder, a pencil, an LED, and a multimeter. We create 2 coiled electrodes from the platinum wire, which we fix to the lollipop stick. We then attach a battery clip and an LED to our electrodes. We add some baking powder to our water to create an ideal electrolyte solution and gently place the stick on the top of the beaker, with the electrodes resting in the liquid. The battery is attached to the electrodes and, as expected, the LED lights up. But when we disconnect the battery, it is still glowing. With bubbles forming on the electrodes, the multimeter confirms that a current is still being produced. But how? In a hydrogen fuel cell, hydrogen and oxygen combine to produce electricity and water. With our reverse fuel cell, touching the battery to the clip causes the water at the electrodes to split into hydrogen and oxygen, a process called electrolysis. You can see the bubbles form at the electrodes when we connect the battery. The platinum acts as a catalyst, allowing the hydrogen and oxygen to recombine. The hydrolysis reaction reverses. Instead of putting electricity into the cell to split the water, hydrogen and oxygen combine to make water again and produce electricity. Can we make our own reverse fuel cell with a few household items? Yes, we can. Wicked challenge smashed. Baseball is considered the national sport of the USA, but how did the baseball glove change from a sign of weakness in a player to become the iconic symbol of a nation's most loved sport? Unlike the bat or the baseball itself, the baseball glove was never originally part of the sport. This is primarily because there was never much need for a glove in the early years of baseball, as the sport was played in a different way. Much of the throwing was initially done underarm, and therefore quite a lot slower than those rapid pitches we see today. However, even as the pitches became hard and fast, gloves were often dismissed. Players considered it a sign of their strength and ability if they risked broken fingers and calloused hands in the name of their sport. So it took a while for the glove to catch on.
There was a stigma attached to gloves. It was quite seen as a manly sport, baseball, so a lot of people kind of went with what God had given them, the hands. And over time, as pitching became faster, as batters became stronger, obviously balls was crashing into your hands at high speed, so players started to develop injuries, calluses, broken bones, bruising.
Simple leatherwork gloves were the first to be used, with fingers removed to ensure ball handling wasn't affected. The first recorded wearer of this small leather work glove was the New Haven first baseman, Charles C. Waite, in an 1875 game against Boston. Although Waite was ridiculed by the crowd and his fellow players, he persisted to use the glove. The Boston pitcher, A.G. Spaulding, noticed and sensed a business opportunity. It inspired him so much that he and his brothers launched a sportswear company, with one of their first products being the baseball glove. Because of Spaulding's great reputation, he was free from ridicule when he first wore his glove in 1877, and with that, the glove began to lose its stigma. With this, the glove began to evolve at rapid speeds. Extra padding was added, as well as webbing between the thumb and forefinger, much like the gloves worn today.
It was approved by the league. I think at the time only pitchers and first bases were allowed to wear them, but slowly it was introduced to all positions within the game.
The baseball glove really has been on quite a journey, but how are these national icons made today? What exactly is a H-web, and why is hot oil so important when making a baseball glove? Nocona have produced ball gloves for baseball since 1934 and use all American hides provided by local ranchers.
We are the only company left in the United States that still has a manufacturing plant here in the States, so we're very unique in a world where we have 80 different brands. We're basically the only baseball glove brand that has their own factory.
Today they make their gloves in their factory in Nocona, Texas. The production of a baseball glove starts with the all-important grading of the leather.
The first step in making a world-class glove is we get the best leather that we can, and that will either be steer hide or buffalo hide and or even kangaroo hide.
The correct amount of leather for the day's order of gloves is selected and then weighed before being moved on to the hydraulic press. Here, the leather is cut into all of the components that will make up the glove. This is done by placing a steel die in the shape of each component onto the leather. A heavy hydraulic press then swiftly stamps down onto the steel die, causing it to cut the leather to the exact shape required. This is a bit like a reverse puzzle for the operator, as he must place each die in just the right place in order to ensure that the maximum amount of leather is used to minimize wastage. Once we have all of our leather components cut, it is time for them to be debossed with their logos, model numbers, and the other important information such as their size. Debossing is essentially just stamping a design onto the leather surface so that it is indented permanently into the leather. More logos are then embroidered onto the leather parts using an embroidery machine that will accurately stitch in the logo. Now that all of the logos have been added to the leather, it is time for the sewing stages. First, the leather bed of the glove is assembled and sewn together. This is all done by highly trained sewers that sew freehand with great skill. Here, the H-web of the glove is being sewn together using a top stitch. H-style webbed gloves are classic styles and have been a staple in glove making for years. These gloves are used in every position on the field, besides pitcher and catcher. The sewing doesn't stop there. The outside glove shell and the inside lining of the glove are assembled and stitched next. This inside lining provides comfort for the glove wearer as well as strengthening the seams, making the glove very durable and able to catch those balls for decades. The outside shell of the glove is then placed onto a jig and turned inside out. This is so the inside lining of the glove can be inserted. Now that the two pieces are together, it's back to the sewing machine, so that the glove can be bound together and the lining and shell are finally joined permanently. Our glove is starting to look ready for a game of baseball. The next stage sees the glove being laced up using leather laces. At this point, the H-web from before is also laced onto the glove. At the moment, the leather of the glove is still a little stiff. To correct this, it must be broken in using a pounder that quite literally pounds the glove repeatedly, relaxing the leather and making it much more flexible in order to make that perfect catch.
We have to take these gloves to a shaping stand where we do hand lasting, and that's a process where we're opening up the inside lining fingers of the glove so that it's going to have that just right feel so that when the customer picks it up in the store, they're going to think, this is the one glove I've been looking for all my life. They will go through a series of processes where they pound the glove and manually manipulate it so that it's got a really nice, good shape to it.
The fingers of the glove are then stretched over hot irons. This opens the finger holes up and sets them in place. Wooden sticks are placed inside the fingers as they cool down, making sure they keep their shape. Just one step left now. All of the gloves are coated with hot oil in order to increase their durability. The oil is applied as a spray in order for a nice, even coverage.
If we were to start a baseball glove and go from one end to the other, so to speak, it would take about 4.5 hours of labor to get it completely to the point where you're ready to go play baseball or softball.
And that's that. Our ball glove is complete, ready to be taken to the field and hopefully enjoy years of winning plays. The baseball glove, a leather-bound, wicked invention. So, there you have it, a dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Turntables, the fuel cell, and baseball gloves, all wicked inventions.